We often hear algorithms described as simple recipes, but in computer science they are much more rigorous. An algorithm is a finite, step-by-step procedure designed to perform a specific task or solve a particular class of problems. Crucially, every step must be unambiguous. This means there is no room for interpretation. The computer follows the logic exactly as written, regardless of the context. Furthermore, an algorithm must eventually terminate. It cannot run in an infinite loop if it is to provide a solution. Think of it as a logical bridge that carries us from a set of input data to a desired output. Whether it is sorting a list of names or calculating the shortest path between two cities, the algorithm provides the underlying structure for the calculation. One of the most important characteristics of a standard algorithm is determinism. This means that if you give the algorithm the same input twice, it will always produce the exact same output, following the exact same sequence of states. Each step in the process transforms the current state into a new state, moving systematically toward the conclusion. This predictability is what allows us to trust software with critical tasks, like processing bank transactions or controlling medical equipment. If the logic is sound, the result is guaranteed. However, the challenge for developers isn't just making an algorithm that works, but making one that works effectively under pressure. In the world of intermediate computer science, we don't just ask, does it work? We ask, how well does it scale? This brings us to the concept of algorithmic efficiency, often measured in terms of time and space complexity. Imagine you need to find a specific word in a dictionary. You could look at every single page starting from the front, which we call a linear search. Or you could use a binary search, splitting the book in half repeatedly until you find your target. While both algorithms reach the same goal, the binary search is exponentially faster as the dictionary grows larger. We often express this growth using big O notation, such as O of n or O of log n, to describe how the running time increases relative to the input size. Choosing the right algorithm is often a trade-off between speed and memory usage. As problems become more complex, we sometimes move away from perfect, exhaustive algorithms towards something called heuristics. A heuristic is a type of algorithm designed to find a good enough solution when finding the absolute best one would take too much time or computing power. You see this in modern navigation apps. The system might not check every single possible backroad between 2 points across a continent. Instead, it uses a heuristic to prioritize highways and major roads, giving you a very fast route that is nearly optimal. From the simple sorting of your email inbox to the complex neural networks driving artificial intelligence, algorithms are the invisible engines of our digital lives. They turn raw data into meaningful action through the power of pure logic.